So in the previous session we have seen the concept of work, and now we will discuss the work done in the case of compression and expansion of a gas in a cylinder, and we will try to understand or justify our sign conventions. So first we will discuss the compression of a gas taken in a cylinder. So you can consider some sort of a ideal gas is taken in a cylinder fitted with a movable piston. The position of the piston is shown in black here. Now there is some sort of pressure inside the system exerted by the gas molecules of the system. Now the figure shows here F external is the external force acting on the piston. So the yellow lines in the diagram shows the initial position of the piston, and when an external force acts on the piston, it will compress the gas inside the system and let the piston be moving from its initial position to the final position by a certain displacement or distance dx here. So you can calculate what is the work done. So you know that in the case of compression the force is external here, so we will say that here work is done on the system by the surrounding. Of course, work is done on the system. So during compression, work is done on the system. Now as per our convention, work done on the system is taken as positive. Let us justify that statement. See, by definition, work done W is equal to F dot S. F dot S. That's our definition, where S is the displacement vector. Okay. So in the case when the displacement is dx, let us say there is a very small work done, or I can call it as infinitesimal work done here. So dw will be equal to, I'm considering the external force to be constant throughout, so I can write F external. So the force here is external force. I'm writing F external dot dx. In place of S here I have got dx here, and you know this F external and dx are parallel to each other, both are to the left in the diagram, so the angle between them will be equal to 0, or it is equal to AB cos theta u format. So Fp dx into cos 0 which is equal to simply F external times dx, since cos 0 is what, 1. Now you know this is what, positive. Okay, so you can see as per our definition, work done on the system is positive, and we are able to justify that statement by using this particular diagrammatic representation. Now let us see how the work done turns out to be negative in the case of expansion of the gas. So now during expansion, work is done by the system. Work is done by the system. Therefore, you can see in the picture, still external force is shown to be acting to the left, and the system's position or system's configuration has been shown here. The initial position of the piston was here, which is denoted by the two yellow lines here, and the gas has expanded, means the piston has moved from its initial position towards the right which is shown by the green arrow here denoted as dx. Now, in mechanics, we are always concerned with the behavior of the system acted upon by an external force. In mechanics, we are always concerned with the action or the behavior of a system under the action of an external force. So you know that automatically when the piston has to move by displacement dx in the direction shown here, there should be a force acting from within. Actually, there should be a force acting from within, which will be directed towards the right, but that is an internal force, or that is a force exerted by the gas on the piston. Now, throughout the process, we assume that we are having some sort of a mechanical equilibrium, or slowly it is very near to mechanical equilibrium, and mechanical equilibrium demands that the process is done quasi-statically. So what happens is that in order to avoid the acceleration of the piston, the external force or the internal force exerted by the gas should be very near to the external force from outside. And who is giving the external force? Of course, the piston will be having its own weight, and that weight will be acting towards the right side, you can say, or you can say there is atmosphere outside. The atmospheric pressure is actually balancing the internal pressure initially. So there is an external pressure from outside or external force from outside, and you can see if this external force, you say that this is some 50 Newton, you say 50 Newton of external force is there, then if internal force is some 50.001 Newton, okay, you can see that I'm just taking very near to the external one. Certainly these two forces are almost equal, you can see F internal and F external are magnitude wise they are almost equal, but the internal force is differing the external force by a very slight amount, so there will be a displacement in the right direction. But remember, in mechanics we usually calculate the work done by or against an external force only. We never consider the work done by the internal forces. So in the same system, or following the same method in thermodynamics also, we are defining dW is equal to, you can see what is the work done by the external force, okay, or against the external force. So that is the way I have to write, work is done by the system against the external force. That is the meaning of negative, actually, against the external force, which is usually the atmospheric pressure or force due to the atmospheric pressure. So what will be the thing equal to? Once again, that will be equal to F external dot dx. That is again the same equation, which will be equal to, it will be F external is towards the left, dx is to the right, so the angle between these two is going to be 180 degree. 180 degree is the angle between the opposite vectors, so it will be equal to Fe dx cos 180, and cos 180 it is equal to -1. So finally you get it is equal to minus Fe times dx, and this negative sign justifies our convention which says that the work done by the system is negative. Remember one thing, there may be a genuine concern here. Actually, is it not the work done by the gas inside the system? And why do we take the external forces as the force here? Shouldn't we have taken the internal force instead of the external force? The doubt is genuine. That is what I justified. We are always interested in mechanics, the work done by or against an external force. Remember, that is why even though there is an internal force acting on the system, on the piston, we have taken the force to be the external force, and luckily, or we can say conceptually, the internal force and external force will be very near to or they will be very near to be can see some sort of an equal value and will be deviating only infinitesimally from the other one, and in that case only you can see the process will be happening quasi-statically and there will not be any acceleration that is caused for the piston. So this is something that we are doing so that we follow the same convention that is followed in mechanics. Okay, so this is the concept that we are following in the case of work done in the compression or expansion of a gas inside a cylinder. Okay, now just remember that you can just think in this way: if these two vectors are in opposite direction, the work done will be negative, and if the vectors are in same direction, the work done will be you can see it will be positive. So I will just conclude with one example. For example, if you have got an object of mass em, see, and if this object is falling down freely under gravity, it is falling down freely under gravity, there is a force of gravity that acts downward. Clear? Okay. Now suppose somebody asks what is the work done by the force of gravity. So automatically you know that the body is moving down, so the displacement of the body is downward, force of gravity also acting downward, so you can say that the work done by gravity, which is external force over here, that will be positive because both Fg and dx are in the same direction. So in this case, work done by the gravity is what? Positive. Now you consider the reverse situation in which the body is just thrown upward. Okay, so the displacement will be dx upward, but the force of gravity, which is the external force here, is still acting downward. Fg is downward. So you can see the angle between the force and displacement here is what? 180 degree. So in this case also you can say the work done by the gravity, it becomes what? Negative. Clear? So you can see that we have calculated or we have determined the work done by the gravity only. Okay, so the work done by the gravity in both of this situation is what? Different in sign. One is taken to be positive and the other is taken to be negative. And you will see that conceptually work done is equal to change in kinetic energy. When work done is positive, work is done on the system. Which is our system? The mass is our system in mechanics here. Okay, work done is positive, so work is done on the system. It should increase its what? Kinetic energy. Work done equal to change in kinetic energy. So you know, in the first case, the speed of the object goes on increasing. Speed is increasing and hence kinetic energy increases. In the second case, since the work done is negative, you can see speed of the ball will be going on decreasing, and you know the speed reduces to zero at the topmost point. So the speed will be going on decreasing in the second case. So that is an example of work done positive and negative. Another example that you can take is in the case of a tug of war competition. The work done by the winning team is taken as positive, whereas the work done by the losing team is taken as what? Negative. So it is based on the force exerted by the teams and the displacement that happens for the tug in the thing. So it's the same thing. In all these cases, we are interested in the work done by or against an external force. So see that is a convention that we'll be following throughout our discussion. Okay, so that's about the way in which you have to calculate the work done. In the next session, we will find out an expression for the work done in changing the volume of a hydrostatic system. Thank you.